So yesterday we talked about relations, and the title of it was Relations and Functions. We never really got to the function part, but today we will. We're going to start right off. So I just called today's lessons functions. Even though it's 2-1, we'll call it functions. So what is a function? Well, I'm glad you asked. I don't normally write down long definitions, but in this case, I think it's important. So a function is a relation in which every element of the domain, I'm not going to make you memorize this or anything, but I think it's good to have it down in writing so that you can refer to it if you forget what it is paired with one and only one. I'm going to underline that. One and only one. So we're really stressing it. One what? Element of the range. That may not make any sense to you whatsoever, but hopefully we'll do a couple examples and we'll see what this really means. All right, so that's a function. So let's do one of those mapping diagram things, right, with the circles and the numbers inside of there, and let's see what it is. So I've got -1, 1, and 3. They put it in a circle. I'm not even going to put it in a circle. Is that all right? I got -3, 1, and 5. Now, you don't know which one goes with what just yet, but they will tell you that -1, oh, I thought I was changing that to red. Oh, that's, clicked the wrong thing. Hold on, give me a sec. There we go. All right, -1 maps to -3, or it relates to -3, corresponds with, however you want to say it, goes with. Then 1 goes with 1. And 3 goes with 5. Now, let's look at the definition. It says, what is a function? We want to decide, is this a function or not? That's what we're trying to do, okay? So it says every element of the domain. Which one's the domain? Right, it's the first ones, okay? That would be the domain, and what would this be? In a mapping situation, mapping diagram. That would be the range. It says, every element of the domain, see each one of these, is paired with one and only one element of the range. So -1 is only paired with -3 and nothing else. Everybody see that? +1 is paired with +1 and nothing else. One and only one. 3 is paired with 5. Again, not with anything else. All right, so is this a domain? Or sorry, not a domain. Is this a function? Yes, it's a function. I'm going to write that whole thing down. It's a function. It's not much different than what we did yesterday. But there was one, remember I said yesterday, one that was a little bit weird, right? One of those things we did yesterday, one of those numbers went to 2 different ranges. Okay, so that would not be a function. So let's do another one. 1, 3, 5. -1, 2, 3, 4. All right. And here's the mapping. Now, you wouldn't know if that's a function right now. Okay. You got to see what it's mapped to. So 1 goes with the 3. So when I say it goes to it, when that arrow goes to it, what is that really? This is an ordered pair, isn't it? So it's just 1, 3. Would you agree? All right, so that's what we're doing. We're just kind of looking at it visually with the arrows, which one relates to what. or which one is mapped to what. Now 3 is a little different. 3 goes to negative 1, and listen to this. 3 also is mapped to 2. So let's write the ordered pairs down. So what does 3 go to? Negative 1, and it also goes to what? 2. And then 5 just maps to 4, and that's it. So we write the ordered pair 5, 4. So is this a function? Does every element of the domain go with only one, with one and only one element of the range? No. Which one makes this not a function? That 3. That 3 goes to a negative 1, and it goes to a 2. It's mapped to a negative 1 and a 2. That's not one and only one element of the range, is it? Okay, it's two different things. So this one x value, this one element in the domain relates to, maps to, goes to, however you want to say it, two different elements in the range. That makes it not a function. So this is not a function. You see that? All right. Let's do another one. This negative 2, 0, 2, and 4. And we only have one thing in the range. But watch this. This negative 2 maps to 4, 0 maps to 4, 2 maps to 4, and 4 maps to 4. They all go with that. So what would my ordered pairs look like? It would be negative 2, 4. It would be 0, 4. It would be 2, 4, positive 2, 4. And it would be positive 4, 4. So those would be my ordered pairs. Everybody see that? Is this a function? It is. Because look, this one right here, this 2, or negative 2, only goes to the 4. Even though that this other element of the domain goes to the same range, and this 2 goes to the same thing, and the 4 goes to the same thing, this is still a function. So I'm going to put yes, it's a function. So that's the one that messes people up a little bit. You think that they all go to one thing, but that's okay. That can still be a function because the negative 2 doesn't go to two different things. You follow me on that? The 0 doesn't go to two different things. The 2, the 4 does not go to two different things. All right? But this 3 right here, that's the one. That's the bad one, okay? It's not really bad. It just makes it not a function because it goes to two different y values. All right? So if you're looking at this, what are we really looking for? We're really looking to see if the, how should I say it? If the x values repeat. So you have a 3 here and a 3 here. If this goes to a number, but this 3 right here, if it goes to a different number, okay, then it's not a function. Make sense? If we were to graph this, in fact, let's graph these ordered pairs. Let's change this back to white. Let's just do a simple little graph right here. There's a little test that we do to determine if it's a function or not, and we can just look at it by the graph. I can just look at the graph, and I'm going to do maybe a couple things we did yesterday and determine if it's a function or not. So watch this. Let's plot these points, and it doesn't have to be super accurate. So 1, 3. So there's 1, 1, 2, 3 right there. This is 3, negative 1, 1, 2, 3, negative 1 right there. This is 3, 2. There's 3 right there. And then there's 5, 4, 3, 4, 5, 2, 3, 4 would be about right there. Notice, what was the thing that did not make it a function? The 3, negative 1 and the 3, 2. Everybody see that? You see this one? There's your 3, negative 1. There's your 3, 2. Now, what is that? It's the same x, but it's different y's. Okay? You with me on that? So it's the same x, but it's two different y's. Look what I could do to this. I don't think I drew this super accurate, but yeah, I'm pretty close. Not perfect, but yeah, that's good. That's good enough right here. Look what I can do. What if I put a vertical line, okay? This vertical line hits two different points, okay? So anytime that you want to see by a graph if it's a function or not, if your vertical line hits more than just one point, then it's not a function. We actually have a name for that, and it's a pretty basic name. It's called the vertical line test. Vertical line test. And what does that test? It tests if it's a function or not. So if it goes through more than one point, if you can draw a vertical line through any of your points. Look, I could have drawn a vertical line. Julie, I'll get you just a second. I could have drawn a vertical line there, couldn't I, through that point? 1, 3. Does it hit any other points in out of these? No. I could have drawn a vertical line through this, couldn't I? At 5, 4, does it hit any other points? No. What if I drew a vertical line right here? This middle one. Yeah, it hits that point and that point. That is enough to say that it's not a function. Julie?
Is it like the pencil test like thing you used to do?
I don't know.
You pass the pencil through the...
Yeah, if your pencil's vertical, right? I mean, you could slant it, right? So that doesn't... So, yeah, your teacher might have called it the pencil test, I guess, but it's got to be straight up and down, okay? Because, so that's why I would rather say the vertical line test, okay? Or the vertical pencil test, however you want to look at it, okay? It's just a vertical line, okay, up and down. Because you could have a pencil that's slanted, and that wouldn't work, okay? Does that make sense? Because look, I could have a slanted line. Let's do that in a different color. I could have a slanted line that goes through here. You with me? But that doesn't mean it's not a function, okay? The line has to be vertical. All right, so let's do another. All right, slide this up. Let's do another. What if you had a line like this? Okay, so you graphed a line, y equals mx plus b, y-intercept, slope, all that kind of stuff, okay? What if you had a line like this? Is that a function? Okay, let's do this. Let's draw a vertical line somewhere. Is there anywhere on this graph, remember it keeps on going too, doesn't it? Is there anywhere on this graph that vertical line is going to hit more than just one point? No, right? Because this is not going to curve back on itself. It's not going to come back around like this or anything like that. Would you agree? So that would be a function. So a linear, well, a line, okay, which is linear, but anytime you have a straight line like this, that's going to be a function because it passes the vertical line test. What if you had something like this? We did this yesterday. Whoops. Remember this from yesterday? We said it was a relation, right? But, and we talked about the domain and range of it. Remember that yesterday? Is this a function? It's not a function. Why? Look, right here it only hits one point, doesn't it? But as soon as you go this way, guess what? It's hitting at 2 points, isn't it? Okay, so if it hits at more than 1 point, all right, then it's not a function. It hits right here and it hits right there. This is not a function. All right, let me do a couple more.
Wait, and the diagonal line is not a function, right?
No, it is. Yeah, because it passes the vertical line test.
So, like, the domains can't be the same, but can the ranges?
Well, on that other one where they all went to 4, 4 was the same for each of the domains. That can be okay. But you can't have 2 of the domains be the same.
So the ranges can be the
and go to different ranges, okay? Yeah, let's do another one. I don't have these in my notes, but what if you had something like this? Now, here's a curve, just like that other one was a curve, but it's curved a little differently, isn't it? Is that a function? Yeah, you can just look at it, and you really don't need the vertical line, do you? But you can see it, right? Look, they intersect all at just one point. No matter where you put that vertical line, you're not going to hit 2 points, are you? Nope. So that would be a function. So yeah, that's a function as well. There's other graphs. There's a slight chance we might do this year. Hopefully in pre-calc you'll definitely do it. We should have gotten to it last year. We were a little bit slow last year. It was my first year teaching it. So you're eventually going to do graphs that look like this. All right? Goes like this and like this. They call this a sinusoid. All right? You ever hear of that? That's okay. Don't worry about it. All I care right now at this point is this a function or not? Is that a function? Yep. Look at that vertical line. It's never gonna, right? There's never gonna be a point on top and the bottom. Agreed? Because it just continues that pattern over and over again. All right. It's not gonna eventually like come back here like this. It's just gonna keep that pattern going forever and ever. So yeah, that would be a function. All right, we good? All right. So it's important. We're going to be doing a lot of stuff later on. Well, in this chapter, we'll be doing a lot with functions. And we're going to do a little bit more with that. I think that's good enough. There's an example 4 that I'm not going to do exactly. We kind of did it already. But there you go. So now, what we're really going to get into today is this function notation. All right. Do you remember how you did problems where you said y is equal, yeah, 2x minus 1, all right? And you might have had a problem that said evaluate this if, and they told you what x was. I don't know, let's make up a number, -2, all right? Do you remember this? All right, so what'd you do? It's just substitution, right? You took that x, you threw it back into this, and you're good to go. So we went y equals 2 times -2 minus 1. That's -4 minus 1, which is -5. So y is equal to -5. Right? We've done plenty of those kind of problems before. Have we done those this year? We haven't done that this year. But yeah, that's definitely something you did, okay, in Algebra 1. I'm sure we'll do a lot of that kind of stuff this year. But now what we're going to do is we're going to take this situation right here. Instead of all of this, there's a way to write it as a function. And this is a function, all right, because it's just a y-intercept at -1, a slope of 2. It's just a nice straight line, okay? So it is a function. Would you agree? Yeah. So there's a way that we can write this. Instead of writing it like this, what we're going to do is write it like this. We're going to use f. We're not always going to use f, but at first we do. And then we're going to put a parentheses and an x. This does not mean f times x. The way we say this is we say f of x. All right, I'll put it in quotation marks because that's how we say it. We say f of x. Everybody with me on that? Yeah, pretty easy. This f of x kind of means the same thing as what the y means. All right, so we just replaced y with f of x. You're like, okay, we've made this way more complicated. Why can't we just keep it a y? It just makes it a lot easier. Well, this actually does streamline it a little bit for what we're going to do. So in this situation, what is our f of x? Instead of y equals, now it's f of x equals what? 2x minus 1. So that's our function, all right? Now sometimes they'll use other letters. Some popular letters, you can use any letter, but some popular letters that they might use is g of x. They might have that, even though g doesn't, function doesn't start with a g. But sometimes they use other letters. They could call it g of x or h of x. Those are kind of like your three common ones that you might use. You could use other letters if you wanted to, but most of the time, at least in high school math books, they'll use f of x first. Sometimes they'll use g of x. Sometimes they'll use h of x. Okay? It means the same thing. It just means the same exact thing. But you got two different functions. If I have two different functions, one you might call f of function. That's my f function. And then you might have a different function, right, different than this. You might call that one the g function. You might have a third one. And what would you call that? The h function, h of x. Make sense? All right. And that kind of differentiates between y equals. If we use y equals all the time, sometimes the next thing, y doesn't equal the same thing. All right, so that's why we do this. Here's how you do the substitution. What they're going to say is they're going to say find, now watch very carefully, f of negative 2. This right here and this right here ask you to find the same exact thing. It's really the same exact problem. It's just the notation is different. The way we write it is different. All right? So let's do that. All right? So instead of saying if x equals negative 2, they just say find f of negative 2. So basically, what did we do with that x? We're just replacing it with a what? With a negative 2. So when you see an x here, what are you going to do? You're going to substitute it or replace it, right, with a negative 2. You see the difference? It's really not a difference. It's the same. You're doing the same thing. The math is the same. It just looks different. It's just packaged just a little differently.
Wait, so we switch out the y, put f of x, and then after we solve the whole thing, we plug the negative 2.
Well, you're not going to solve the whole thing yet. You're going to. This tells you to plug the negative 2 in for the x. So this, finding f of negative 2, is kind of, instead of saying evaluate if x equals negative 2, instead of saying all that, they just say find f of negative 2. See how it's a little more compact? It's a little bit more streamlined, all right, than what we've done before. But it means to do the same exact thing. So how would I do this? Well, find f of negative 2. So all I do is take negative 2 and substitute it in for that x. Everybody see that? Because I changed that x to a negative 2, so I'm changing this x to a negative 2. So the math is exactly the same as what we just finished doing. All right, negative 4 minus 1, negative 5. So there you go. So I would say that f of negative 2 is equal to negative 5, instead of saying y equals negative 5. All right. Let's do an example. We kind of did an example, but that was like a pre-example. Let's do an actual example. Example 5. That's in the book. All right, and they tell you that f of x is equal to 3x minus 5 this time. And what you want to do, now, this kind of flies in the face of what I said earlier, but let's just do it like this. Well, they do this. They say, here's the domain. Here's all the possible values for x. Oops, that's a terrible brace. Exactly, all right? So they use the word evaluate, which is unfortunate because I said this function stuff kind of takes away that word evaluate. But they're using the evaluate to mean evaluate this for this is my domain. So it's really like 3 questions, all right? So they're saying find f of negative 2. Then they're saying find f of, what do you think? 0. And then they're also finding f of 4, okay? And that's what they're asking you to do. Does that make sense? All right, yeah. So what are you doing? You're just plugging that negative 2 in for what? In for that x. Okay, so I go 3 times negative 2 minus 5. Negative 6 minus 5, negative 11. Put in a 0 now. All right, so 3 times 0 minus 5, which is equal to Domain are your x's, right. Remember, the domain are all the x's, and this is an x. So we're sticking that in for the x, we're sticking that in for the x, and then we're sticking that in for the x. We good? All right. Let's do f of 4. So I'm just taking that 4 and throwing it in for the x. So it's 3 times 4 minus 5. 12 minus 5 is 7. And then that's your value there. Okay? All right. When do we get out of here? 25? All right. I just have enough time. Now, we're really going to make the notation. What's that? You didn't do that already? Now we're really going to make the notation look pretty crazy. Now you're going to feel like you're in Algebra 2. Stop talking. There we go. So here's what we're going to graph. And the notation is really nuts. But after a while, you kind of get used to it. A lot of this stuff is kind of fluff. You don't really need it that much. At least that's what I call it. F or x, and then they're going to put g of x. Now, I'm going to put this vertical bar. That little vertical bar right there, it actually has a meaning. It means such that. So in math, when you put that one single vertical bar, that means such that. So we're graphing f or x, comma, g of x. Remember the f of x, g of x, h of x? It's just basically the same thing as saying what? The f of x, g of x, h of x. It's the same thing as just saying it's the y value. Remember that? Remember I said earlier? Okay, it's just replacing the y. And that's what this is saying. So it's saying graph a point, or graph all the x's and y's, okay? And again, they make this real fancy, but it just means the same kind of stuff that we've always been doing, all right? So graph an x and a y such that g of x, or y, right? Think of it as the y equals negative 1/2 x. Now, would you be able to graph that? Y equals negative 1/2 x? Sure. What's the y-intercept? Y equals mx plus b. You haven't forgotten that, right? We did a ton of that in geometry. Bunch of that in geometry. What's the b? No. 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 B is not the x. The b, what's being added to this? No. No. The half is being multiplied by it. What's being added to it? Thank you. 0. 0 is being added to it. So what's the y-intercept? No. We just said it. What's the y-intercept? This is the y. I'm getting a little frustrated here. This is the y-intercept. Okay? No, I didn't. This is the y-intercept, where it crosses the y-axis. What's the y-axis? Okay, or what's the y-intercept? It's 0. What's the 1/2? Everybody's saying 1/2 when I ask for the y-intercept. What's the 1/2? That's this. What's that? That's the, yeah, what is the m? It's the slope. It's the slope. You guys forgot that already? We did that 1,000 times last year. All right? So this is your slope. This is your y-intercept. So if I was to graph it, I'll graph it nice and neat in a second. This is just sloppy graph, okay? So what's the y-intercept? Right here. What's the slope? Negative 1/2, right? Negative 1, 2, boom, right here. And then we connect them. Agreed? All right? It just looks fancy. All right? It's the same thing as this. It just looks a little different. But they're going to add one more thing. They're going to put a comma, and they're going to give you a restriction on the domain. So remember that line I put arrows at both ends? Well, this one is not going to continue forever in both directions. All right? They give you a restriction. They say that x is between -2 and +4, and it could include both of those. So this is kind of a combination of what we did yesterday and stuff that we've done in the past with graphing. So let's put a nice graph on here. In fact, the domain is a restriction on what x's we're allowed to use. We can't use every single x in the world. That means our graph's not going to keep going in both directions. Remember yesterday we talked about the domain?
Yeah. So we
Okay.
in all the numbers in between -2 and 4, like how we did.
So what? Yes. So watch. X has to be between -2 and 4. So where is -2? On the x-axis? It's right here, correct? And where is 4? 1, 2, 3, 4. It's right here, okay? But what I'm going to do, remember how I did my graph and I stuck those 2 arrows on the ends? All right, that's if you didn't have any restrictions. But now we can only go between -2 and +4. So let's graph this first. Okay, what's the y-intercept? It's 0. What's the slope? -1, run 2, right? You with me? Now normally, now don't draw this whole thing that I'm going to do right here. Normally, we would draw it all the way out to here, wouldn't we? But not now. Why not? They've restricted us. We can only use the x values between -2 and +4. So let's see where we have to start and end this thing. Here's -2, but where is it on the graph? It's right there, isn't it? Everybody see that? So we can't go any further to the left. So what about all this stuff? All this stuff, hold on just a second. We can't include all that stuff. So what am I going to have to do with this graph? It's going to have to go to here. It's going to be short. It's going to be a line segment, isn't it? All right? And then how far can we go in the positive direction? To 4. So where is this going to go? Right here. Do you see that? So then we got to shorten this up. We can't use all of that. We're going to pull that back to right there. So this is the graph of this. Now this looks crazy, doesn't it? I mean, if you would have walked in the door and said you're going to learn this, you're like, that's way too hard. But it's not that bad. This just says, basically, find the x and y's that work for this, but are between -2 and 4. That's all that says. Okay? No, you don't have to put in every single number. I've already done that with that line. That line represents every single number between -2 and 4. Just the graph. Yeah, that's what it says, to graph it. Okay? Your homework is 23 to 35. Same section, but you're doing some more. I collected it already. So it's late. All right, so there it is. 2-1B, 23 to 35. And there you go.